Last time we solved a circuit that contained several batteries and using Kirchoff laws, okay? Just to remind you, this is what we had. We had this circuit with three different batteries here. And remember at the very beginning, we had chosen these directions for the currents I1, I2, and I3. And when we solved, we found that I2 and I3, the values we got from solving the equations were negative. That is telling us that the directions we had picked for I2 and I3 were incorrect. So then we redraw the circuit with the correct directions. So I2 is actually going this way, the correct I3 is going this way, and I1 is going that way. And those are the values with 3 sig figs that we had found. Now, something interesting is happening here that we didn't see before when we had only one battery in the circuit. Notice that in the case of the first battery here with an EMF of 9 volts, the current is actually flowing into the positive terminal of the battery. Whereas for the other two batteries, we have a current flowing out of the positive terminal. So there's something special about this battery here. What is happening is that, well, normally this is not what you see. You never see that when you have only one battery in a circuit. But those two batteries, the second and the third one, are actually strong enough to push the current into that direction here. Now, some batteries are not designed to absorb a current flowing that way, and they will just start to heat up, and eventually it will melt if you don't stop the circuit, if you don't turn off the circuit. But some batteries can actually uh, take a current flowing this way, and what will happen in that case is that a battery in that case will actually absorb energy from the charges and get recharged. This is what happens when you boost a dead battery of a car using another car. You actually use the strong battery to push current into the positive terminal of the dead battery, and this one gets recharged. So this, we call that, when the current flows into the positive side, positive terminal, we call that a charging battery. If it's designed properly, it's being recharged. And in that case, this battery here is actually absorbing energy from the charges. So those two batteries here, we'll call those discharging batteries. They're giving energy to the charges. But this battery here is taking energy away from the charges. So what happens in this circuit is that E2 and E3 are giving energy to the charges. Those charges flow in the circuit. Some of them lose energy in the battery to recharge it, and other charges will lose energy, and charges also lose energy in the resistors, where energy is converted into heat or light. So the source of energy for the circuit are E2 and E3. Those two batteries here are giving energy to the charges, and then this energy is given off away by the charges through the three resistors and also through this battery here. Okay, so the discharging batteries are giving energy to the charges, and then the charges are giving energy away inside charging batteries and in resistors. Okay, let's see how to make that more precise. First, let me rewrite the values of the currents with 4 sig figs because we just want to be more precise in our calculations. These are the values we had obtained previously. Okay, now the next thing is I'm going to just relabel. There's nothing very deep here or important. I'm just going to rename the three currents IA, IB, and IC instead of I1, I2, I3. It just makes some equations a bit less confusing. And I'm just reminding you of the three values here. That's what we found last time. Okay, now we're going to check that energy is conserved in this circuit. So how do we apply energy conservation? Remember before, when we had only one battery in a circuit, we were saying that the power in the battery must be equal to the sum of the powers in the resistors. But now we have several batteries. Some of them are charging, some are discharging in general. So what's the rule? In that case, we must have the sum of the powers in the discharging batteries. That's energy given to the circuit, to the charges by those batteries. That must be equal to the sum of the powers in the charging batteries, which are taking energy away from the charges, plus the sum of the powers in the resistors, where charges are also losing energy through heat and light. So on this side of the equation, we have the sum of the total energy per second given to charges in the circuit, And on this side, you have the total energy per second uh, that is transferred from the charges to some external source of energy, either in the form of energy stored in a battery or in the form of heat or light um, because of the resistors. So this is the equation for conservation of energy in a general circuit. Okay, so let's check that in our circuit. Let's go back here. So here, now we know this battery here is charging. By the way, when we tell which battery is charging or discharging, we must draw the currents in the correct directions. Of course, at the very, very beginning, when we start to solve the circuit, we had picked this direction up here, this direction here up, and IC to the right. And we knew that some of those directions were incorrect. You cannot use those directions that you picked randomly at the beginning to decide which battery is charging or discharging. That makes no sense because you're choosing the directions of the currents any way you want. It's only after you redraw the correct directions of the currents that you can tell which batteries are actually charging, which are discharging. So in our case, those are the correct directions of the three currents. We can tell that this battery here with an EMF E2, this one is discharging. The current is flowing out of the positive terminal. E3 is discharging also, and E1 is a charging battery. Okay, so the discharging batteries are the second one and the third one. Those are the ones that are giving energy to the circuit. And the charging battery is there's only one, it's E1. This one is taking energy away from the charges. Okay, now that we have identified the charging and discharging batteries, we can apply conservation of energy. We can check conservation of energy. Okay, here's the circuit again. Okay, so first we're going to calculate the total power given to the charges, to the circuit by the discharging circuit. The power in the second battery here, okay, is given by 12 volts multiplied by the current flowing here. And the current flowing here is just what we call IC. So you do IC times E2. Okay, and I'll just remind you that IC was that value here. So you multiply IC, the current through the second battery, multiplied by its voltage, and you get this value in watt. So this is 0.3365 watts given to the charges by the second battery. The third battery is also discharging, and we calculated its power. It's given by E3 multiplied by the current that flows through that battery, but the current flowing here is what we call IB. So IB times E3, you do the multiplication, you get 7.991 watts. And that's it. There's no other discharging batteries. So the total power transferred to the charges by the discharging batteries is the sum of those two numbers that gives which gives 8.327 watts, which now I'm done. I'm going to round that off to 3/6, 8.33 watts. That's the amount of joules of energy per second transferred to the charges. Okay, now let's find how much energy per second is given away by the charges to the charging battery and to the resistors. So the power in the first battery, which is charging, we just do the current flowing here, IA, multiplied by the voltage of the battery, which is E1. So IA times E1, that gives 5.047 watts. Okay, how much power is in each resistor? In the first resistor, I do R1 times, I could work with the voltage, but it would be, I don't know what's the voltage here, so it would be long to calculate the voltage here, but I know the current here, so I'm going to use the formula for power given by Ri squared. So I do R1 times this current here, which is Ia squared. You calculate that, you get 1.572 watts. That's the amount of energy per second that is dissipated in the resistor. It's energy that is transferred into heat or light. Okay, now we repeat for the second resistor. We do R2 times the current that flows through R2, which is IB squared. So we do R2 times IB squared, we give this power. And to the third resistor, we do R3 times IC squared. That gives this really small power. And then we add everything. If energy is conserved in the circuit, as it should be, The sum of all those values here should be equal to the power that was given off by the two discharging batteries, which I remind you was equal to 8.327 watts, which we rounded off to 8.33 watts. If you add all those four values here, you get 8.328 watts, which, because we're really working with 3 sig figs, I round off to 8.33 watts, as expected. So we have shown that energy is conserved in this circuit. It should be conserved. If here, when we did this calculation here, we had some number that are different, and we had got a different value than 8.33 watts, and while we had before for the discharging batteries, we did find 8.33 watts. If this number was not equal to the power given by the discharging batteries, that would tell us that there's a mistake in our calculation. So some of our currents are incorrect. So we just made a mistake when we solved the circuit. Power has to be conserved. If it's not, it's because there's something wrong with the solution and there's a mistake in our calculation. But here, that's a very powerful test of all our currents. If some of our currents were wrong, we will see right away that we will not have got the same power as in the discharging battery. So this is a very powerful test that we indeed have the correct currents for this circuit. Thank you.